All right, here we go. So we have been discussing in 4.2, we discussed single sample t-tests, and now we're going to be doing paired t-tests. So what is a paired t-test and how does that compare to a one sample t-test? So a paired t-test, you can see it a couple of different ways. It can be called paired, dependent, or two sample t-test. And it's a t-test that compares two sets of data or the change or difference in that data. So when can you run a paired t-test? You can run a paired t-test when the sets of data match up. So a couple of different types of t-test data or paired testing is pre-test and post-test for students who are taking an exam. Medication, you can do like any blood pressure before medication, blood pressure after medication. So those are different types of t-tests that you can run. So here are steps to running a paired t-test. Number one, state the null and alternative hypothesis. Those we did with our single sample t-test, so that's exactly the same. What is different is that our null hypothesis states that the average difference in population is equal to 0, meaning that there is no change from the original sample to the second sample. So that means right here, this is the average, or the difference in the averages equals 0. So really we may be looking at two of the same sample. Like if I'm doing pre and post test, it would be of the same student, right? So are the same students, is their difference 0? And then my alternative hypothesis is that the average difference in population does not equal 0. So that indicates that there is a change from the beginning sample to the second sample. So this is the mean differences in the population does not equal 0. So these will be our typical null hypothesis and alternative hypothesis. Select the appropriate significance level and check the test assumptions. So remember, our test assumptions are that we have individual samples, in that it's randomized, right? We talked about conducting random sampling. And again, our significance level is 0.05, or thinking of that 95% confidence level. Third step, analyze the data and compute the test statistic. Okay, so number 3, analyze the data and compute the test statistic. So this is going to be very similar to when we did our original t-testing. Degrees of freedom, again, is n minus 1. Thinking about n as the number of pairs, not the actual, it's from test 1 to test 2, how many pairs are there? And then we have some new variables here. SE with a subscript of D, this is the standard error of the differences. Standard error of the differences, and we'll learn more about this as we do our example. All right, here's our standard deviation of the differences, that S with a subscript of D, and a couple of equations that we need to know. Standard error, we know this formula. Standard error is this standard deviation divided by the square root of n, the number of sample, or the sample size. And this, we know this test statistic formula, except this is new. This we had as X bar. It's the same idea, but it's the sample mean difference. So we're gonna need to be finding the difference from our sample 1 to our sample 2. This is our mu with a subscript of D. So that's the hypothesized or claimed difference. And the claimed difference we know is going to be 0 for this paired test, and then divided by our standard error. So next, we're going to interpret the results. So the first result that we could interpret is to reject the null hypothesis. So is it within the rejection region? So thinking about our little graph, here's our rejection region is in the tails. And then our fail to reject region is between those values. between our critical values. So reject the null hypothesis is that the difference between the observed sample mean and 0 is too great to happen by chance, meaning it does not equal 0. And then the fail to reject is the difference between the observed sample mean and 0 is probable. So it's within that boundary line of your T critical values where it's probably just happened by chance if it is not exactly 0. All right, so examples of paired t-tests, we talked about this a little bit a second ago, comparing pre-test and post-test scores, comparing measurements taken under two different conditions, measuring hearing loss in a subject's left and right ears. Go ahead and add your own example. We're going to be sharing this in class together. So yeah, think about things that you could test, especially over time, and then write that down. All right, flipping to the back here, we're going to do a sample paired t-test. So here's our example here. Researchers want to know if coffee increases systolic blood pressure. In order to determine the effect of coffee on blood pressure, they measured participants' blood pressure, then had participants drink a 12-ounce coffee and measured blood pressure again. Conduct the appropriate analysis to determine if participants' systolic blood pressure is higher after drinking coffee. So they want to know, was there a change in their blood pressure before they drank coffee and after they drank coffee? So assume the data was collected randomly and independently, so our assumptions are met, and our significance level is 0.05. So let's go through our steps here. Our first step is to state the null and alternative hypotheses. So remember, our null hypothesis is that the difference equals 0, meaning that there is no difference in blood pressure after drinking coffee. There's supposed to be an R there. All right, and then our alternative hypothesis is that the mean difference does not equal 0. So that means that there is a difference in blood pressure after drinking coffee. All right, just for good measure, let's state our significance level. So our significance level, remember, is our alpha, and alpha is going to be 0.05. So remember, our confidence level, we're always going to use that 95%, right? Okay, so let's figure out what the values of our variables are. So this is standard deviation of the difference. Well, in order for me to find standard deviation of the difference, I have to find the difference when they drink coffee and when they don't drink coffee. So let's calculate the difference first. So difference here, and all I'm doing is subtracting coffee minus no coffee. And I'm going to put it next to our table here. You don't have to draw the lines, but I want to draw them just so you can see. So 128 minus 24, that's 4. 118 minus 110 is 8. 2, -2, 10, and 8. So we have our different values. So now we're going to run it just like we would run a normal t-test, except we're using the difference values. So these are the values that we're going to be plugging into our table to find standard deviation and mean. So I'm going to go down to my new document. And I'm going to add lists and spreadsheets, and I'm going to plug in my values. All right, I have 6 values. That's good. Oops. All right, so here we have our one variable stats. Our X bar or our mean is 5, and then our standard deviation is 4.52. So let's fill in the values that we know here. Standard deviation is 4.52. Degrees of freedom, remember, is n minus 1. So our n, we have 6 values. So 6 minus 1 is 5. This is square root of 6. And this is our, in the calculator, it's going to look like X bar, which we found is 5. The claimed value or the claimed difference, remember, is 0. And our t critical value, we need to use our t table to find out. So our degrees of freedom was 5. So I'm going to follow 5 over to my 95%, and it's 2.571. So my critical value is 2.571. All right, now let's compute our test statistic to see if there was, in fact, a change or not. So we're going to be reminded that our formula is the difference, the average of the differences minus the claimed difference divided by the standard deviation divided by the square root of n. So let's plug in our values. We have 5 minus 0 divided by 4.52 over the square root of 6. So I like to go ahead and set myself up for success. So I'm going to plug in my fraction first. Then we have 4.52 and the square root of 6. We get 2.71. All right, so that's my t statistic. Well, let's see what that value means in reference to our t critical value. So we know that in the middle we have 0, and then my boundary lines are 2.571 and negative 2.571. So remember, our fail to reject region is in here in the curve. And this is remember, our critical region. So the critical region is the reject region. And then our fail to reject is here. So where does 2.71 fall in our distribution here? Well, it falls outside in our critical region. So we know that it falls in our reject region. So what does that mean in context of our coffee drinking? So that means that there was, in fact, a change. So this fail to reject region tells me that there was no change in the blood pressure, in the systolic blood pressure after drinking coffee. But in my reject region, it tells me that there was, in fact, a change given the sample that they took. So what does this mean when we interpret our results? We're going to write a sentence for ourselves. Since the t statistic value is 2.71, which is more extreme than our critical value, which was 2.571, we have evidence to reject the null hypothesis and suggest that drinking coffee does increase blood pressure. So I know some of you are thinking, well, we proved it wrong, but their initial hypothesis or their initial assumption was that it did change, which we in fact proved that it did change, because the fail to reject region would be that it did not change. So our T statistic value is more extreme, therefore we rejected the fact that it did not change, and we're suggesting that drinking coffee does increase blood pressure. All right, so make sure to come back to class tomorrow with your own example. I want to hear what you have to say, and I'll see you soon.